This is the 8th and final video in the Essential Extract Vector Calculus series. In this video, we're going to talk about the divergence theorem. If you watched the previous video, then you saw how Green's and Stokes' theorems are two-dimensional generalizations of the fundamental theorem of calculus. The divergence theorem can be thought of as a three-dimensional generalization of the fundamental theorem of calculus, and it can also be viewed as a generalization of Green's theorem. As always, a link to the Summary of Vector Calculus handout is available in the video description. By the end of this video, we will have covered everything on this handout. Hopefully, it will serve as a concise reminder to you of all of the major topics in this essential extract. To begin this video, let me remind you of the three equivalent forms of Green's theorem that we discussed in the previous video. There was the original form of Green's theorem, what I called the vector form of Green's theorem, and what I called the divergence form of Green's theorem. In the vector and divergence forms of Green's theorem, the function F is a vector field from R2 to V2, and the vector n was a normal vector to the boundary of D. For details of these equations and how we derive the equivalent forms of Green's theorem, please see the previous video. In the previous video, we saw that the second form of Green's theorem generalized in a natural way to give us Stokes' theorem. In a similar way, the third equivalent form of Green's theorem generalizes in a natural way to give us the divergence theorem. The statement of the divergence theorem is rather easy to read. It says that the triple integral over a solid region E in R3 of the divergence of a vector field f is equal to the double integral over the boundary of E of f dot ds. I'll break this definition down for you in just a minute, but one thing which you might want to remember now is that the surface integral on the left-hand side is a surface integral of the second kind. The definition of the double integral over the boundary of E of f dot ds is the double integral over the boundary of E of f dot n ds. This is a surface integral of the first kind. Seeing this helps to understand that the divergence theorem is a direct generalization of Green's theorem to one dimension higher. Let's take a closer look and make sure that we understand the statement of the divergence theorem. As mentioned, the integral on the right-hand side is a triple integral over a solid region E in three-dimensional space. The integral on the left-hand side is a surface integral of the second kind. It's being integrated over the boundary of the solid region E. As with Green's and Stokes' theorem, the circle on the double integral on the left indicates that the boundary of E is being taken with the positive orientation. If you've forgotten what that means, you can see video number 3. Finally, notice that just like with the fundamental theorem of calculus and Green's and Stokes' theorem, the integrand on the right-hand side is something which involves derivatives of the integrand on the left-hand side. These observations can help you to understand what this theorem is saying. As usual, we do need to make some technical assumptions in order to ensure that the theorem holds. For example, we may want to assume that the solid region E is a bounded region with piecewise smooth boundary, and we may also want to assume that the vector field f has continuous first partial derivatives and some open region which contains E in its boundary. As with Stokes' theorem, the divergence theorem has a very nice physical interpretation. It tells us that the flux of a force through the boundary of a solid region is equal to the triple integral of the divergence of the force over the region. It's easy to understand why something like this should be true just from basic physical principles. So it's nice to know that the mathematics agrees that this is a correct observation. In the previous video, we saw that Stokes' theorem guaranteed the equivalence of the differential and integral forms of 2 out of 4 of Maxwell's equations. One application of the divergence theorem is that it proves the equivalence of the differential and integral forms of the other two of Maxwell's equations. The equations that we're referring to are Gauss's laws for the electric and magnetic fields. The differential forms of these laws are written on the left-hand side, and they can be easily derived from basic physical principles. The equivalent integral forms of these equations are on the right-hand sides. To see why the differential and integral forms of these equations are equivalent to one another, just compute the triple integral of both sides of either one of these equations over a solid region E in R3. The divergence theorem tells us immediately that the triple integrals of the left-hand sides of these equations are equal to the surface integrals that you see in the integral forms of the equations. That demonstrates very easily the equivalence between the differential and integral forms of Maxwell's equations. In this video series, and especially in the final two videos, we've seen a tower of generalizations of the fundamental theorem of calculus. It's natural to wonder whether there might be even higher dimensional generalizations of Stokes' theorem and the divergence theorem. To conclude this series, I'd like to tell you that there is such a generalization, and it's called the generalized Stokes' theorem. The statement of this theorem is a little bit too complicated to squeeze into the end of this video, so I'm going to have to leave it for another time. In any case, I hope that you enjoyed these videos and I hope that they were useful to you. Please feel free to leave me any feedback in the comments below. Well, that's the end of this video series. Thank you for watching and feel free to check out some of the other videos on my channel.